In this video, we'll find out how much you remember about exponential functions and logarithms. So first we've got a section here that deals mostly with understanding the definition that a logarithm is an exponent. So when it's spelled log and there's no base, remember then it is called a common log and our base is 10. So really what you're being asked here is what exponent would you put on 10 if you wanted to get a result of 1. So when you're looking for a logarithm, you're looking for an exponent. So when it's spelled natural log, as in number 2, then we know the base is e. So this problem is almost too simple. When the base is e, we're saying what exponent should we pick if we want to get a result of e. So we obviously need an exponent of 1. So that would be an identity property of logarithms. In number 3, we want a base of 2. What exponent would turn it into a result of 32? So that happens to be 2 to the 5th. In number 4, we have to do a couple of steps. So we want a base of 8 and we want an exponent that turns it into, our base is 8. I want a question mark there. We want to turn it into a 1/2. So let me start by rewriting that 1/2 as a 2 to the negative 1. And that might give you a better idea here that negatives are reciprocals. You might actually prefer just leaving it that way, whatever. The idea here is I can break an 8 down into a 2 by doing its cube root. So remember that a 1/3 power is a cube root. So if I did a 1/3 power, that would turn the 8 into a 2. And then if I want to do a reciprocal, I would do a negative. So our exponent is negative 1/3. Take the cube root and then flip it over to do its reciprocal. All right, and here we've got another common log. And most students, good science students, just say count the number of decimal places you're moving it backwards. Or we could read this carefully: tenths, hundredths, thousandths, 10,000, 100,000ths, 1 millionth. But again, we know that this is 10 to the negative 1, 2, 3, 4, 5, 6 places. So just like you would do with scientific notation. In number 6, our base is 1/4 and we want to turn it into an 8. Well, let's think about this step by step. What could we do to 1/4 here with an exponent? Well, the first thing we could do is a negative, and that would turn it into a 4. And then we actually have to break it down to a 2 to raise it up to a 3rd power. So we could actually do its square root to change the 4 into a 2 and then cube it. So the 3 parts of an exponent: the negative is the reciprocal, the denominator is the root, and the numerator is the power. So I hope that you can follow some of these just by observation. But let's take another look at that one, perhaps algebraically. We want an exponent on 1/4 that will give us a result of 8. So here you might like the algebra method of writing these both as base 2. So 1/4 is 2 to the negative 2 power, and 8 is 2 to the 3rd power. So if you're having trouble finding any logarithm, this of course would be change the good method, change them to the same base. So now power of a power we would multiply. So this equation is equal if our exponents are equal. So do you see that there's another way of coming up with the exponent? Okay, continuing on here. Natural log. So remember that you've got some options here. The log of a power is the power times the log, so we can bring that 3 in front. And then the logarithm of 1 over e is the same as a negative 1. So you could do this in multiple steps if you wish. So you could say, well, now let's do this power of, and bring that power down in front again. Eventually you're going to come up with a negative 3 here as the exponent. And here we have an inverse property, e raised to the natural log of 5. Think what the natural log of 5 is. The natural log of 5 is an exponent that you would put on e to turn it into a result of 5. So what happens if you put that number on e? Of course, you get 5. So inverse property. And here we've got the logarithm of a logarithm. So let's work inside the parentheses. So what's the natural log of e to the 5e power? So again, remember that this exponent can come down in front of the logarithm. So we could change this inside the parenthesis to look like this. And the natural log of e, of course, what exponent on e turns it into e? That's just a 1. That's our identity property. So we've got now the natural log of 5e. So the log of a product becomes the sum of two logs. So this log of a product becomes the sum of two logs, and the log of e is 1. So we could write our answer here as 1 plus natural log of 5. You could use a calculator to round that off, but that's the exact answer. Okay, notice our directions here for these equations, no calculator. So our answers, we're just going to leave them in exact form. So here we're back to the same idea we had a minute ago. These numbers are both base 2. So 16 we can write as 2 to the 4th. And then we can use our power of a power property. So remember that power of a power, we multiply the exponent. So this side has an exponent of 4x minus 12. And we would need it to be equal to this exponent. So 3x is 12 and x will be 4. In the next one, how do we get a variable out of an exponent? We change it by taking the logarithm of both sides. So this step you will skip probably in the future, because you'll remember now your log property that the log of a power is the power times the log. So that's the reason that this works. To get a variable out of an exponent, take the logarithm of both sides, and then the power becomes the coefficient. So now we can rewrite this. So most students say the exponent can come down in front of the logarithm, but the correct property would be to say the log of a power is the power times the log. And the natural log of 7 and the natural log of 5 are, of course, constants. So let me divide. And then we can solve this for x. So a little bit of algebra. We're going to subtract 1 from the right side. So your answer might not be pretty, but it's a number. And then we divide it by 2. So to divide by 2, you could multiply each term by 1/2. So you could write it like this. No need to get a common denominator. That answer would be fine. Let's see if I can transfer it up here before I scroll back. All right, so that was my value for x. In 12, we already have logarithms, and we've got the difference of two logarithms. So there's another one of our log properties. The difference of two logs came from the property of a log of a quotient. Remember, the log of a quotient becomes the difference of two logs. So if I reverse that property, the difference of two logs, let's put it back into a quotient, because you can see in this case we get a nice term of 2x. All right, does that help us? Well, it's a little bit simpler now. We only have one logarithm. The natural log of 2x is equal to 7. So now, how can we solve when our variable's in the logarithm? Then we change to exponential form. So we always use inverses. If we start with exponents, we change to logarithms. If we start with logarithms, we change to exponents. So when there's only one logarithm here, this is just use your definition of a natural log. So this says e to the 7th power produced a result of 2x. So we can solve for x. X is e to the 7th divided by 2. So with a little bit of practice, Students might think these are difficult because the answers don't look like simple integers. But once you get some review of the properties of logs, these are pretty simple equations to solve. So number 13, I see the sum of two logs. So let's see if we get anywhere if we put that back. So where did the sum of two logs come from? It comes from the log of a product. So let me rewrite this. Let me reverse the property. So now I could rewrite this as the natural log of x squared minus x. And again, how do I get a variable out of a logarithm? I change it back to exponential form. Natural log has a base of e. So this says e to the first power is equal to x squared minus x. Well, unfortunately, we're not finished here, and students might particularly dislike where we're headed here. This is a quadratic equation, so we set it to 0. E is a constant. That is not factorable, so we go to quadratic formula. X is equal to, the opposite of b would be 1, plus or minus the square root of b squared minus 4 times a is 1, times c is negative e, all divided by 2a. So you could stop at this point. Remember, as long as you have an answer that no longer has any numbers in it, or you could rewrite this in some form. I could put the 1/2 and I could split this up. This is 1 minus or 1 plus 4e now. So whether you leave it as a single fraction or whether you split it up, there's one technicality here that you shouldn't leave when you do your final answer. We shouldn't keep both the plus or the minus. So this is a step students will often forget. Remember the domain of natural log? The domain is 0 to infinity. Can you picture the graph of natural log of x? So remember that we can't do logarithms of negative numbers. So we're going to throw out the negative. We're going to throw out the negative answer because it would give us negatives in the original statement. So sometimes you got to pay attention a little bit more closely than you think to the domain of the original problem. So we would keep only the positive answer. And just to show you that you did not have to split that up, I'll put it back into this monomial form. Doesn't matter if you leave the 2 as a single denominator, if you split that up into 2 fractions. But important idea here, keep only the positive. All right, in our next equation, we've got variables in an exponent. So we know we want to use logarithms to solve. To get variables out of an exponent, take the logarithm form. So this one, by definition, tells us that the natural log of 6 was the exponent 2x plus 4. Or you could say I'm taking the natural log of both sides. Doesn't matter. So now we have some simple algebra here. We're going to subtract 4 and divide by 2. So pretty simple once you get used to the idea that your answers aren't going to be integers. And in 15, find an inverse function. Well, let's change this to y form. Let's rewrite this. All right, so to do its inverse, use your definition. So we can say that e to the, let me rewrite that. E to the y is equal to the result, 5x plus 3. And now remember what we want to do is reverse our variables. So we want to solve this backwards. So if you change your variables here, so if we make this x turn into y and this y turn into x and this x turn into y, and then we solve it. So we want to keep the y by itself, so we would want to subtract the 3 and then divide by 5. So there's one way we could write that, or we could now write it as perhaps 1/5 of e to the x minus 3/5, either one of those forms. All right, our video is getting a little long here. Let's see if we can quickly remember. We've done these recently, so I think we can zip through our graphs fairly quickly. Remember that e to the 0 power, any positive base to the 0 power is going to produce 1 as our key point. And then of course here we have the point e comma, or 1 comma e, and then 2 comma e squared. Why does the graph fall here? Because e to the negative 1 power is 1 over e, and so on. All right, so our transformations, remember when we put a negative with the x, that is a horizontal reflection. And then a negative outside the function is our vertical reflection. And then we're adding 1. So this is going to shift the whole graph up 1 unit. So I'm going to start with the graph we had in question 16. And then we're going to do a horizontal reflection. So now our graph would be going this way, still through 0, 1. And then we're going to take that graph and do a vertical reflection. So it would go down to negative 1. So now the vertical reflection would be through the point 0, negative 1. And then we're going to slide it up 1 unit. So it looks like our final graph is going to have its asymptote at y equals 1, and it's upside down. And our key point here moved to the origin, 0, 0. All right, the logarithm function, inverse of e to the x. So instead of having a horizontal asymptote, it has a vertical asymptote. And remember, the exponent that produces 1 is always 0. So we always, for a natural, or for any logarithm, whether it's natural log or any other base, we have a key point of 1, 0. So now our transformations, we're going to add 2 to the x variable. So we're going to shift 2 to the left. And then we're going to do the opposite. So there's our vertical reflection. So we're going to start with the graph that we had in number 18. And we're going to, which had a key point of 1, 0. We're going to go left 2 units. So our key point moves to negative 1. And our asymptote used to be at x equals 0. So our asymptote also moved 2 places to the left. And then be careful before you... There's the graph shifted 2 places to the left, but don't forget now that we have to do our vertical reflection. So our final graph would be this solid graph. All right. Some domain and range questions here, so similar to what we were just graphing. This plus 3 moves the graph 3 to the left, and then we flip it upside down. So let's say that it goes here. This key point would go to negative 2, and our asymptote went over to x equals negative 3. And then the negative sign flips it upside down. And then this plus 2 moves it up 2 units. So our key point should be at negative 2, positive 2. And this would be our graph here with a vertical asymptote for a logarithm function. So our domain looks like it goes from negative 3 to infinity because we shifted it to the left. And our range would go, for a logarithm function, is all real numbers. So you don't necessarily have to sketch the graph if you can follow that transformation process. All right, here we have an exponential function. So again, what I'm thinking through here is I start with my e to the x graph. I'm going to add 1 to the x, so we compensate for that. So we're going to shift that 1 unit to the left. So our key point now is at negative 1 comma 1. And then this negative 2 takes it down 2 units. So we're going to have our vertical asymptote used to be at y equals 0. So our vertical asymptote also moves down 2 units. And our key point shifted left 1 unit and right, shifted left 1 unit and down 2 units. So it is at negative 1, negative 2. All right, so Our domain for exponential functions are all reals, and our range is everything above our horizontal asymptote. And that should do it.